Today is Saturday, 31st of May 2025, 6 a.m. Eastern Time. This science and technology update is brought to you by Preeti Capital, your trusted source for intelligent insights.
Okay, let's dive right in. We got your sources on the Earth's core, and, well, our mission today is to really unpack them.
Sounds good.
Find the key insights, maybe the surprising bits about this incredibly important part of our planet.
It's a fantastic topic. The core is, literally central to so much. And like your sources show, it's not static at all, it's dynamic.
Yeah, definitely not just a dead lump down there. The picture I'm getting from these is um, complex, but the basics seem pretty clear, right? Mostly iron and nickel.
That's the main takeaway, yeah. Iron and nickel. But crucially, divided into that solid inner core and the liquid outer core.
And that division is key, because that liquid outer part, that's where the magnetic field originates, according to these papers.
Precisely, that's the engine room
Right.
without it. Well, life up here would be, let's just say, very different, if it existed at all.
Right. So the plan is dig into each layer, figure out how that magnetic field gets made, how we even know any of this since we can't exactly, look, and why it matters to you listening.
Makes sense. So starting at the very center, the inner core.
Let's do it. Okay, your sources. They put its size at about 12,220 kilometers in radius, roughly.
Yeah, about the size of the moon, give or take. But incredibly dense, of course, and buried under thousands of kilometers of rock,
Composition. Mostly iron and nickel. That seems consistent across the board.
dominated by iron, yeah, with nickel. Though, interestingly, one of the sources you sent mentioned possible lighter elements mixed in too, adds a bit of complexity.
Okay, and the real head scratcher.
Yeah,
It's solid, even though the temperatures are, what, over 5,000 degrees Celsius?
some estimates go higher, yeah, even up towards 5,700 degrees, hotter than the surface of the sun in places.
So why solid? That feels wrong.
It's the pressure. The sources really hammer this home. The sheer weight of everything above it creates pressure that's just astronomical, over 3 million atmospheres, maybe 3.5 million.
Wow.
And that immense pressure basically squeezes the atoms so tightly they can't transition into a liquid state. They're locked in place despite the incredible heat. Pressure wins.
Planetary scale pressure cooker, like you said.
Hmm.
Okay, now this is interesting. One source mentioned potential complexity within the inner core, an inner core.
Ah, yes, that's fascinating stuff. It comes from looking closely at seismic waves. The idea is the iron crystals might be aligned differently in the very center compared to the outer parts of the inner core.
So variations in structure.
Exactly. Anisotropy, meaning seismic waves travel at slightly different speeds depending on the direction they pass through. It hints at, well, a complex history and maybe even ongoing growth as the Earth cools.
And didn't one source also hint it might be spinning slightly differently, not quite synced with the rest of the planet?
That's the idea of differential rotation, yeah. The data is tricky, but there are suggestions the inner core might rotate just a fraction faster or slower than the mantle and crust above it.
Adding to the whole dynamic picture, it's not just sitting there.
Not at all. It's a very active place, deep down.
Mind-boggling. Okay, so surrounding this super pressurized, possibly layered solid ball, we have the outer core. What did the sources say about its dimensions?
It's a much thicker layer, about 2,300 kilometers thick, starts around 2,900 kilometers down, and goes to the inner core boundary, roughly 5,200 kilometers deep.
And same stuff, iron and nickel.
Pretty much, yes. Still mostly iron and nickel, but the huge difference, the critical difference, is that it's liquid, molten.
A giant ocean of liquid metal.
Exactly. And this is where the magnetic field gets generated. This is the geodynamo's home.
Right, the geodynamo. How does that work, according to your sources?
Wow.
How does moving liquid metal make a planet-wide magnetic field?
It's basically down to convection. You've got this huge body of molten, electrically conductive metal. There are temperature and density differences, so the hotter, lighter stuff rises, cooler, denser stuff sinks. It's constantly churning.
Okay, like water boiling in a pot, but metal and huge.
Kind of, yeah. But because it's moving conductive material, this motion generates electrical currents, massive electrical current.
And that creates magnetism.
It does, but it needs structure. Just random churning wouldn't create a stable, large-scale field. That's where Earth's rotation comes in. Ah, the Coriolis effect.
Exactly. The planet's spin organizes these convective flows, sort of aligning them into columns or spirals. This organized flow of electrical currents is what generates and sustains the Earth's main magnetic field.
So solid center, liquid metal ocean churning around it, organized by spin, creating this field. Okay, the big question then. Why does this matter to us up here on the surface? What's the payoff for you listening?
Well, the payoff is huge. This magnetic field stretches way out into space, creating the magnetosphere.
Earth's force field.
Pretty much, yeah. It acts as a vital shield.
Shielding us from what?
Primarily the solar wind, this constant stream of charged particles flowing from the sun,
Yeah.
and also high-energy cosmic rays from deeper space.
Without that shield?
Those particles would bombard the upper atmosphere. Over long timescales, they could strip it away, like what might have happened to Mars.
So the magnetic field is literally protecting our air, protecting life. Absolutely. The sources make that link very clear. It's fundamental for maintaining a habitable planet with a stable atmosphere.
Mhm.
And, on a practical level, it's why compasses work, but it also affects navigation, communication satellites.
And the auroras, right, northern and southern lights?
Exactly. That's the solar wind interacting with the magnetosphere made visible, a beautiful consequence of deep Earth physics.
It really is amazing. Something so vital happening thousands of kilometers down, totally invisible.
Uh-huh.
Which leads to, how on earth do we study it? We can't drill there.
No, not even close. The main tool, as your sources emphasize, is seismology, studying earthquake waves.
Right. The waves travel through the earth.
And how they travel tells us what they're passing through. There are different types of waves, P waves and S waves mainly.
Okay, and they behave differently.
Yes. P waves are compressional, that sound. They can go through solids and liquids, but they change speed. Scientists notice they slow down dramatically when they hit the outer core,
Indicating liquid.
and then speed up again when they reach the inner core.
Showing it's solid again. Clever. And S waves.
S waves are shear waves. They wiggle side to side. And the key thing is they cannot travel through liquids. Liquids can't sustain that shearing motion.
So if they hit the outer core,
They starp. They disappear. The fact that there's an S-wave shadow zone on the opposite side of the Earth from an earthquake was the definitive proof the outer core is liquid.
that's ingenious. Using earthquake echoes as a kind of planetary ultrasound.
It really is. And techniques like seismic tomography, which one source mentioned, use data from thousands of earthquakes and seismometers to build up quite detailed 3D maps of the core and mantle structure.
Are there other methods mentioned in the sources? Besides seismic waves?
Yeah, they also mentioned high-pressure experiments,
Yeah.
using things like diamond anvil cells to squeeze tiny samples of iron and nickel to core-like pressures and temperatures in the lab.
To see how they behave.
Exactly. And also computational modeling, running complex simulations on supercomputers to try and replicate the fluid dynamics of the outer core and the geodynamo process. Advanced imaging was mentioned too, likely tied to refining seismic data.
Okay, so understanding our core. It's not just navel-gazing about Earth, is it? Your sources suggested it connects outwards.
Definitely. Understanding our geodynamo is key to planetary science in general. Why does Earth have a strong field? While Mars basically lost its global field billions of years ago, why is Venus's field so weak?
It helps us understand what makes a planet potentially habitable.
Precisely. Does an exoplanet need a magnetic shield to hold onto an atmosphere and support life? Studying our core helps us frame those questions and evaluate discoveries elsewhere. It also tells us about Earth's own formation and how it's evolved over billions of years.
Wow. So the deepest, most hidden part of our planet holds clues about life elsewhere and our own origins.
It really connects the very small scale, material physics under pressure, to the grandest scales of planetary evolution and astrobiology.
Okay, this has been a really insightful journey pulling from your sources. We've gone from the solid inner core through that churning liquid outer layer, seeing how it generates the magnetic field that protects us all.
And looked at the clever ways scientists figure all this out from the surface.
Yeah. Hopefully it's clear just how connected we are to that deep, hidden engine. It's running constantly, miles below, making life up here possible.
Absolutely essential, even though we never feel it directly.
So here's something to think about, a final thought. Knowing about this incredibly active, dynamic core deep beneath you, does that change how you perceive Earth? Is it just rock underfoot? Or does knowing about its turbulent, molten heart make it feel more like a living, breathing system in a way? Something to mull over.